All right. So today we're going to continue our discussion of mathematical preliminaries. I know I said last lecture that it would be kind of an unusual one in the sense that we'd be spending a lot of time just focusing on mathematical definitions and things like that, and that the whole course wouldn't be like that. Well, that's still true today, although we have a few additional things that are worth defining, still kind of within a somewhat rigorously mathematical treatment of things. So we're going to continue along that same trajectory, and again, I'll encourage you to adopt sort of a mathematician's mindset. And don't think of it so much as mathematics at this point. I think, mathematics is probably, commonly regarded as just being the domain of numbers and how to manipulate numbers and things like that. But mathematics is a lot more rich than just numbers. It's really a language used to describe things in the real world. And I think that really holds true in today's lecture as we discuss this notion of sets and spaces, which are really mathematical constructs that are intended to provide some kind of language to describe things that we can categorize, things that we can measure, and things that we experience in our day-to-day lives. So that's really kind of where I want you to think of things, almost in a little bit more of an abstract way, as we kind of go through this notion of sets and spaces, and you'll have some common interpretations and prior knowledge probably of how these concepts come to bear in things like vector spaces when you're describing points in some kind of three-dimensional space, let's say. But it so happens that these same ideas, and in particular, the notion of defining some kind of physical space, has sort of an abstract analog as it applies to describing functions. And in fact, it's possible to construct a space that is basically spanned by some set of functions. And that's especially important as we dive into this subject of finite element methods and how do we choose to find solutions to problems of particular interest where those solutions happen to be themselves functions, and how we describe functions, how do we categorize them, those things become particularly important. So that's kind of the motivation behind why we're going to talk about some of these things and provide these definitions in more detail. But before we even get to sets and spaces, I wanted to actually conclude on a few topics that we left off on in last lecture when we were discussing tensors, kind of the end subject that we left on last lecture. So we had some notion of scalars, vectors, and matrices, these kind of variable dimensioned arrays of numbers, where a rank 0 tensor we defined as basically just a single number, or a scalar in our terminology that we used. We defined a rank 1 tensor as basically a one-dimensional array of numbers, or a vector. And tensors also had this interesting property that not only were these, they generalized to arbitrary kind of rank, so to speak. So a rank 2 tensor is a matrix, basically a two-dimensional array of numbers. A rank 3 tensor is a three-dimensional array of numbers, or kind of like this weird cubic array of numbers. Rank 4 is sort of an array of arrays, which is sort of hard to conceptualize, but mathematically, there's nothing that prevents us from defining such an object. And the main thing that I wanted to kind of come back and point out is that, all these constructs, all the notion of a tensor really does have a connection to a physical object, in the sense that always when we define any tensor of whatever rank, generally speaking, we limit the range of components of each one of these different tensors to basically ranging over some kind of sub-index that ranges from a value of 1 to 3. And the 3 is important here because 3 is intended to be representative of physical space, or 3 dimensions, the space that we live in day to day. And so in that sense, tensors really do have a direct connection to the physical world. And basically, you'll see a little bit later in the course where and how these specific entities come into the picture in describing different physical quantities of interest. Perhaps you already have a good sense of that, or maybe you've had previous coursework that kind of dived into some of those subjects. But I do want to also point out that some of the operations that we defined from the previous lecture, including things like defining an operation to multiply basically a vector by a matrix, that operation kind of generalizes actually quite nicely in the case of tensors. And all these operations can be written in a way where I can describe what are the resulting components of this new vector C that is obtained by multiplying the matrix A times the vector B. If I wanted to know what are the individual components of this vector C, I can express that using C sub I to indicate the specific sub-indices in this vector, ranging from 1 to 3 if it's basically a rank 1 tensor or a vector living in a three-dimensional space. And it so happens that this idea of representing not just these kind of abstract kind of notational representations of tensors in this kind of boldface font with all these kind of intermediate operators defined, it's sometimes more convenient and actually helps to clarify exactly what's going on by just saying, let's not even write this kind of expression here. Let's just say what the components of this resulting operation are by considering doing some kind of summation operation over kind of distinct pairs of indices. So I can write what are the resulting indices in this vector according to a summation of aij times bj summation over subindex j, where j ranges from j equals 1 to 3. And it so happens that various people over the years, including Einstein himself, of the theory of relativity, among other contributions to science, came up with this kind of notational convenience that basically said, if you're working with tensors and you have these situations where you're multiplying one tensor by another, and there's sort of a summation operation happening over kind of a repeated index in an expression like this that involves the product of two tensors, then the rule states, according to Einstein's summation convention, that if there is an expression that looks like this to describe these components, whenever there's a repeated index or subindex in these expressions multiplying two tensors, then it is simply implied that there is a summation happening over the full range of values of j ranging from 1 to 3. So in effect, according to this notational convention, I could write out explicitly this big summation symbol to indicate that I'm actually taking a summation over all values of j ranging from 1 to 3, assuming that there are two values of j that appear in this kind of expression for the components. Or I could just be lazy and omit it entirely. So all I would do to express that this component ci is in fact equal to this expression is I could just omit this and then write aij bj, and it's understood that there's this implied summation over the subindex j. This actually is quite convenient when generalizing other types of tensor operations or multiplication operations, especially for higher order tensors or tensors of higher rank. So if I wanted to say, not just define some kind of matrix vector multiplication to get some new vector, I could also define a tensor multiplication operation that takes some rank 4 tensor, let's say, and multiplies it by some rank 2 tensor, a matrix, in order to get some new rank 2 tensor. And the convention that I'll adopt to define this new kind of tensor multiplication operation between a rank 4 and a rank 2 tensor will look something like this, basically, where I'll have a summation over some subindices k and l, which range from respectively 1 to 3, involving these kind of subindices of these two different, variable rank objects. And again, according to the Einstein summation convention, I could write it, including these big summation symbols that are kind of hefty and a little bit cumbersome to work with, or I could just omit them. And by the Einstein summation convention, it's just presumed that if I write Cij equals Aijkl, Bkl, then there's this implied summation over k and l, each of them ranging from 1 to 3. All right, so that's, in a nutshell, index notation or Einstein's summation convention. And that's going to become particularly relevant later on when we deal with things like, how do we define relationships between stress and strain? Two objects which in a uniaxial sense, are relatively easy to relate to one another. You probably well remember from, I think it was the second lecture, we introduced this relationship between stress and strain, a constitutive relationship that assumed linear elastic behavior. And that relationship was well defined if, let's say, we had only uniaxial states of strain and stress that we cared about. So if we had, in other words, some uniaxial bar that we were stretching along its axial dimension and which kind of manifested in some kind of axial stress across the cross section of this kind of axial member. But in general, stress and strain are quantities that are not strictly uniaxial in nature. You can have solid objects that can be subjected to much more general states of stress and strain. And in fact, we won't go into the details of how exactly we construct those representations. We'll provide a brief review in a later lecture. But the main idea is that in the end, what we'll find is that both stress and strain can actually be represented as these rank 2 tensors, or these kind of 3x3 matrices consisting of a bunch of components. You may have seen this in your undergraduate strength and materials class, but it certainly comes into focus now. And more specifically, if we want to relate, how does this rank 2 tensor of these kind of like 3x3 array of components of stress, how does that relate to this 3x3 array of components of strains? And it so happens that the relationship between those two objects is governed by this kind of tensor operation where C, sometimes called the constitutive modulus matrix, is actually this rank 4 tensor object. Again, we'll kind of go through some of the details, but I wanted to present a little bit of a preview so you kind of know where and why are we even discussing tensors. At the end of the day, we need to incorporate this notion of a rank 4 tensor, kind of like I'm showing here, as an array of arrays, in order to be able to relate individual components of a strain tensor characterizing the state of deformation in maybe some block of material to the resulting state of stress that would act on all the different kind of exposed faces of this three-dimensional cube. So in the end, it's a useful construct. You can represent that relationship in a way that invokes this definition of a rank 4 tensor. And there are simplifying ways where you don't have to necessarily rely on the use of a rank 4 tensor object, but I think it's particularly nice and it clarifies some of those details. Okay, so with that, let's move on to the main subject of today's lecture, which is sets and spaces. And some of this, again, may just be a review, but I just want to present a little bit of a preliminary set of definitions, just to kind of clarify in your minds what's the notation that I'm going to use for this class, and how does that kind of reconcile with some of the notation you might have seen in some of your other courses. If you've taken any courses in statistics or other kind of related domains, you probably already have a good idea of sets and how that comes to bear in a variety of different domains of interest. But a set, as I'll define it in this class, is really just a collection of distinct objects or elements, not to be confused with finite elements, the subject of this class, but really elements in the case of the definition of sets really just refer to distinct kind of things that I can put into these groupings. And the most common use of sets is to organize distinct sets of numbers. So common definitions of sets include the set of all real numbers. And real numbers are just, any number you can think of, kind of like we discussed in the previous lecture. It could be 1, it could be 2.4, it could be negative 3.8, any number you can think of ranging from negative to infinity to positive infinity. Those are all real numbers. And the set of all real numbers usually is just denoted with this kind of, blackboard font, capital R. There are other sets of numbers of practical interest, like the set of all integers, this kind of blackboard Z, which ranges from all the negative integers, ranging from minus infinity to positive infinity. There's also the set of natural numbers, which could include or exclude 0 among them, but generally it refers to the positive set of all integers. So you can write out these different sets as basically, explicitly anyways, some kind of curly bracket expression that encloses basically just a list of all of the objects that are contained in that particular set. For example, the set of all natural numbers is basically just, curly braces, 0, 1, 2, etc., encompassing basically all of the positive integers. And there's also some other notation just to clarify. If I say that a particular number belongs to a given set, I'll use notation that looks like this, where I have this kind of funny looking, almost E kind of character, which is basically just a notation that says that this number belongs to this particular named set, where I've defined it previously and given it some kind of specific definition. If I have a cross through that symbol, it just means that number does not belong to that set. So for example, 2.4, which is a real number, a fractional number, does not belong to the set of integers, because clearly it has this kind of decimal part. All right, so that's the basics of sets. And there's a variety of ways that you can define sets. The simplest way is to just explicitly list all of the elements that belong to a particular set. So if I wanted to define some new set of numbers, which I'll call A, I can create this new set by just creating a set of curly brackets and then list off all the elements or the numbers that belong to that set. In this case, 916, which happens to be my my area code for my very first phone, just for giggles. All right. Another way of defining sets is to actually use something called a set builder notation, which is kind of a shorthand way of identifying some set of numbers that belong to some set that you're trying to define. And you start by first enclosing some of these details within curly braces. Usually when you're defining sets, it's always within curly braces. And then you say, I want to define this new set, which I'll call R plus. I'll call it the set of all positive real numbers. That's what I want to define. I can say that this set should consist of all values X or all numbers X that belong to the set of real numbers, but that includes all the negative real numbers. I don't want those. So really what I want is the set of all numbers X that belong to the set of real numbers, such that, or, given that, those numbers also satisfy this extra condition that I'm specifying, such that X is a strictly positive number. And I can include this kind of vertical bar basically as an additional kind of just notational thing to just say, this is a condition. I want to define a set. It should consist of all the real numbers, but such that they also satisfy this extra constraint. And that's a particularly nice way of building up sets of numbers or sets of objects that have to satisfy these additional constraints that you might impose on them. Another simple way of defining a subset of maybe some larger set of numbers is to use interval notation, where you might just say, here's a square bracket to denote, I want to define the set of all real numbers, or really the subset of all real numbers that range between a value of 0 and 1. And if it's clear, at least in the context of how you're defining this, you can use this kind of square bracket to denote, I want to define all numbers, including 0 and 1, that range basically over the set of real numbers. And I can use this kind of subset notation to indicate that I'm referring to basically not all of the numbers in the space of all possible real numbers, but just kind of a subset of them, just a handful of them of particular interest. So different ways that you can define sets using these different notational kinds of things. And sets aren't restricted to just numbers. In fact, sets can also be used to assemble all kinds of different things, sometimes kind of funky, weird things. I'll give the example of using sets to actually list off people in this class. For example, if I wanted to create some new set that just has all of the people in this class, I can, list off S, the number of the students in this class, and then I can list off all of your names, basically. I can also create simple sets that only have one kind of entry in them, such as the set containing the single teacher in this class. I guess that would be me. And you can do other things. You can create set unions, combine them. So the union of all students in this class and the taken in addition to the single teacher in this class is basically everybody in this class, all the people in this class. Conversely, the set intersection operation is basically considering, what elements belong to both of these two different distinct sets. And if there's no shared elements between those two sets, as in the case of this example, I basically refer to the null set or the empty set, which is basically a special set that doesn't contain any elements at all. So again, all really just notational preliminaries and giving you some kind of ideas of how sets are put together and how sets can be manipulated in other ways. But the real utility of sets, to be quite frank, is not so much in categorizing these kind of funny other objects. Usually it's to define conventional spaces as we're used to thinking them. So spaces of numbers are commonly, things in one dimensions that can be just the set of all real numbers. So also, you could think of that as the real line. It's sort of like a one-dimensional space, if you will. There's also the set of all points in two-dimensional space. If you like, that's sometimes denoted capital R squared, basically. And really, the way to think of this is not that we're talking about some kind of graph or a plane. Really, when I'm talking about R2, what I'm referring to is it's a set. It's a set that contains all of these individual distinct points positioned everywhere in this kind of space. And, at least if we just define this set in that fashion, there's really no distinct association between these points. I'm just kind of bundling them all up and putting them into this big object, which I'm calling R2. So the set of all those numbers consists of basically all of these kind of two-dimensional positions in space. And I can represent those positions, in fact, as vectors, as we did in the previous course or in the previous lecture. R3 obviously generalizes quite nicely if I wanted to describe the set of all points in a three-dimensional space, and I can represent that using a three-dimensional vector. So for R3. All right, so that's, spaces in 2 dimensions and 3 dimensions, or sets of points if you prefer. And I can use this notation, this kind of set-like notation, to identify not just whole spaces that encompass all of the possible points that exist in 2-dimensional space, for example. Sometimes it's useful to identify subsets of a particular, full R2 space and say, maybe I don't really care about all of the points in 2-dimensional space. Maybe I only care about some subset of points that define some object of interest. And that could be useful if you're trying to, say, define some structure or some kind of solid object that you're trying to determine what are the stresses inside of this solid object. So commonly, if you're trying to restrict attention to a particular subdomain, I'll usually use this notation where I'm referring to any particular subdomain of interest using this capital omega. And in general, omega will be some well-defined subset of some larger kind of 2-dimensional or 3-dimensional space, depending on the particular problem we're looking at. All right. So if I'm referring to all the points that belong to this set, really what I'm looking at are all the points X that belong to that subset of capital omega. All right, so that's sets, subsets in kind of 2-dimensional space, 3-dimensional space. The other thing that I want to go over is this notion of basis vectors. All right, so if you're talking about 2-dimensional spaces, 3-dimensional spaces, this is a concept you're probably already familiar with, but it's the idea that really, if I'm looking at the set of all possible points that lie in some 2-dimensional space, let's say, I can characterize where those points sit in some kind of larger space in terms of their coordinates, or in other words, in terms of their relative coordinates measured relative to some, let's say, x-axis, and maybe their coordinates measured relative to some y-axis. Just to kind of make things a little bit funny, I'm just going to denote x and y are going to be x1 and x2. Not to confuse you more, but that's the notation I'll choose. And in general, I might have, aligned with these two different axes in this 2-dimensional space, I can define 2 vectors, which are strictly aligned with each of those 2 coordinate axes. And I'll define these 2 vectors, the so-called basis vectors of this 2-dimensional space. And I'll denote them E1 and E2. And these 2 vectors actually have some special properties as well. I'll define them in a special way where basically they'll look kind of like this. The components of this particular vector E1 will be 1, 0, indicating that it's a vector pointing along the x1 direction with no component pointing in the x2 direction. And similarly, E2 will point strictly vertically in the x2 direction. They'll have unit length, which is to say, if I were to measure what's the length of this vector, what's the length of that vector, it'll have a length of 1, so it's been normalized, such that if I were to compute what's its norm, or what's the length of each of these two vectors, I guarantee that that length is 1 for both of those two vectors. And they are mutually orthogonal, which is to say that if I took the dot product, or the inner product between these two vectors, in other words, take the entry-wise product and sum up all of those kind of individual products of the individual components of these two vectors, sum together, they should all equal 0. So in other words, I ensure that these two vectors are really not at all aligned. They're pointing in strictly perpendicular directions relative to one another. This notion certainly applies in 2 dimensions. You can think of how to generalize this idea to the case of a 3-dimensional space. And in fact, it generalizes to spaces of arbitrary dimension. We're not just restricted to 2D or 3D. We could go all the way up to Rn if we really like. But the idea of coming up with this set of independent basis vectors to describe, basically these different coordinate directions in some n-dimensional space is really useful for representing, general vectors as some combination of the basis vectors. And that's really the utility of defining these sets of basis vectors. Really, their utility applies to defining where exactly does a particular point sit. If I wanted to know where is the location of this particular point X, I can represent it as a vector in terms of its components, or I can actually represent it as a linear combination, as it's sometimes described, of these two basis vectors. And it so happens that if these basis vectors are mutually orthogonal, if they have unit length, then the representation of this linear combination of E1 and E2 to come up with this new vector X is simply proportional to each of the two basis vectors multiplied by the corresponding projected components of that vector on each of these two kind of coordinate directions. Applies in 2 dimensions, applies in 3 dimensions, applies in arbitrary dimensions up to order n, basically. So I can basically express any vector or any point that lies in some n-dimensional space as simply a linear combination of the individual basis vectors that span that particular space. So that should be, reasonable to understand. All I have to do is know what the individual components of this vector are, and then sum up those components multiplied by the individual basis vectors to reconstruct that particular vector of interest. All right, so that's linear combinations of basis vectors to come up with particular descriptions of points. Now I want to come to the subject of spaces and particular properties of spaces. Still on this kind of abstract notion of what exactly is a space as compared to a set, I defined a set as really just a collection of numbers. There was really no specific association between individual points, and there was no notion of distance between individual points. In order to kind of come up with this notion of distance between particular points in some set of positions in maybe a 2-dimensional space or a 3-dimensional space, I really have to define how do I measure distances between two different distinct points in some kind of space of points, or how do I measure distance between abstract objects? In fact, these kinds of notions of a space, and a metric space in particular, really comprise just defining some set and then also defining some kind of function that I can use to measure the distance between the different elements of that set. In the simplest case of, let's say, a vector space, a vector space is a particular case of this sort of vector space that allows you to define maybe some n-dimensional space, Rn, maybe it's a 3-dimensional space, for example, and some corresponding way of measuring distances between points in that three-dimensional space. And the conventional way of defining distances in a 2D space, a 3D space, is to use this description of the vector norm or the vector length. So if I have two vectors, let's say A and B, and I say that both vector A and vector B lie in this, let's say, two-dimensional vector space that's shown in this figure, I can measure what's the length of this kind of vector A. I can measure what's the length of this vector B. Or I could define some new vector by taking A minus B, which basically gives me this new kind of, tip to tail kind of representation, A minus B, and I can compute what's the length of this new vector, A minus B, which basically should give me the distance between those 2 points in this two-dimensional example. So the distance between point A and point B are defined through this kind of normed length kind of definition. So the conventional definition of a normed vector space is really just a collection of points, let's say, in some kind of set of points in some continuous space, for which I have this measure or this kind of way of measuring distances between points. And it has to satisfy some interesting properties. Obviously, the distance from any point to itself has to be equal to 0. That one should be pretty obvious. The distance between any 2 points that are not the same has to be a strictly positive value, so you can't have somehow negative distances appearing. It shouldn't matter if you kind of permute the order of these things, if you have A minus B or B minus A. So if this vector is pointing this way or if it's pointing that way, the length of that vector is the same, even though its orientation differs. And then finally, the triangle inequality, which is kind of a fun one. It basically says that the distance to go from A to B plus the distance to go from B to C is always going to be greater than the distance that it would take to go from A to C directly, which is kind of a fun thing. There's some geometric interpretations of that, but really it has kind of a nice visual interpretation. In general, if you could draw a triangle that says the distance from A to B, the distance from B to C can be represented in this kind of graphical two-dimensional sense, then really it kind of stands to reason that regardless of where you pick this position B, it could be here, it could be here, it could be, over here. It doesn't really matter. It's always possible to show that the distance to go from A to C directly is always going to be less than or equal to the distance from A to B and then B to C. So just a few extra properties of this notion of a vector space, how we define distances between points, and that's particularly useful if you want to, say, measure distances between points in physical space, in a three-dimensional space. But that's not really where the utility of this notion of spaces ends. And as I mentioned at the beginning of this lecture, I said that one of the utilities of being particular in defining these notion of sets and spaces is that I can put other kinds of fun objects into sets or define spaces consisting of objects that are not strictly numbers. They're not strictly positions in some kind of 2 or 3-dimensional space that has physical intuition behind it. I could also define sets that consist of functions, which is kind of a building block for this notion of spaces of functions. So several examples of sets of functions might be the set of all kind of monomial functions, or in other words, the set of functions consisting of, x squared, x cubed, x to the fourth, and so on. I can define a set that basically just consists of all those different functions defined kind of independently as independent elements in this new set that I've defined. And conventionally, I'll use this notation where if I'm defining a set that comprises some collection of functions, I also want to be particular about what's the range of values over which this set of functions is defined. So if I wanted to define some set of functions, which I'll call M, the set of all these monomial functions, I'll also be particular and say that I'm only defining these functions, I'm only interested in their outcomes or their values within the range of x between 0 and 1. So for all x between 0 and 1, I define this set of functions that has well-defined values within that particular interval. So that's kind of the notion of a set of functions. I can also, rather than monomials, I could choose some other set of functions, like a set of sine functions. And if you're familiar with the notion of a Fourier series, which is basically a way of representing some function as some kind of linear combination of sines and cosines, effectively, you're using this notion of a set of functions to construct some representation for a new function as just some particular combination of these different, specific functions belonging to a given set. Now, where this all kind of comes together is in this idea that not only can we define sets or collections of functions in the same way that we define sets or collections of numbers or points in a multidimensional space, rather we can abstract this idea of a space. Rather than defining some physical space, I'm actually going to define a space that is kind of comprised of some set of a bunch of different functions that could be constructed by combining some particular set of basis functions. So in the same way that I described a vector space as being basically a way of describing all of the possible points that exist in some n-dimensional space, which are representable as some kind of linear combination of all the basis vectors defined in that space. Or in other words, I can represent any point x as basically some coefficient or coordinate x1 times the first basis vector plus the second coordinate times the second basis vector, so forth. So I can represent any point as a linear combination of these basis vectors. In an analogous fashion, in a function space, I can define this space of possible functions that can be constructed through some combination or linear combination of these so-called basis functions. So for example, building off of the previous example, I could define some set of functions, x squared, x cubed, and I could define maybe the set of all possible, basically third order polynomials, omitting kind of the leading constant term, that could be constructed by basically just choosing different coefficients to prepend each one of those different monomial function terms. So I can come up with the space of all possible functions that look like this, and where these different coefficients, C1, C2, C3, I can just pick those almost like I'm picking them from some kind of three-dimensional vector space, if you like. So the cool thing about this idea of saying, let's come up with a new way of constructing functions as just linear combinations of these kind of basis functions, however we've defined them. The nice thing about this is that we've kind of recast our interpretation of constructing functions as linear combinations of basis functions such that they kind of inherit a lot of the same properties as conventional vector spaces. And vector spaces, like we discussed a moment ago, certainly provide you with a way of labeling where does this point exist in some three-dimensional space, but it also provides me with a way of measuring how far away are these 2 points from one another in this three-dimensional space. It so happens, in the case of function spaces, we can also define a similar notion of distance, or kind of distinguishing different functions from one another by coming up with some way of measuring how different is this function from this other function, provided they're represented in this kind of way as a linear combination of some set of basis functions. And as a consequence of that, what we find is that a lot of the common properties that we see and which apply in the case of vector spaces to define things like the inner product or the dot product between 2 vectors gives us a sense of how close are these 2 vectors to one another. If 2 vectors are not at all aligned with each other in some three-dimensional space, then we expect the inner product or the dot product between those 2 vectors is going to be 0. And if they're perfectly aligned, then we expect the dot product or the inner product between those vectors is going to be a larger number. Using this notion of a dot product,
we can then construct what's a measure of length of a particular vector, such as in the Euclidean norm or the distance norm defined for vectors, as we did in the previous lecture. And building upon this notion of distance, we can then construct some measure of distance between two distinct points by simply using this same definition of a norm and then just saying, well, if I want to measure the difference between two particular points A and B, I just take their difference to construct a new vector going between them, and then I measure what's the length of that new vector. All of those concepts generalize and apply in the case of function space. In fact, if I have, let's say, two functions, f and g, and I wanted to know how similar are these two functions, f and g, I might want to define a similar operation as for this kind of dot product or inner product for vectors. I can define this notion of an inner product for functions in the following way. I can say the inner product between two functions, f and g, is defined as basically the integral over some domain omega that I might be interested in. Let's say it ranges between x equals 0 and x equals 1, just to make things a little bit more concrete in your mind. I can define the inner product between these two functions over the interval from 0 to 1 as basically just the product of those two functions multiplied by each other, and then take the integral of that product over the full domain over which they're defined. And that's the so-called inner product defined for functions. Using this definition, I can then go ahead and say, well, now that I have a way of defining some inner product between functions to tell how similar are they, I can use that same definition of an inner product in an analogous fashion to how I defined length in the context of vectors of points in three-dimensional space. I can apply that in the case of measuring the length of a particular function, or kind of give me a measure of how big is this function in kind of a normed sense. And the particular norm of interest in this case is the so-called L2 norm. L2 because effectively we're taking f times itself in this integral, so we get f squared in the end when we're computing the norm or the magnitude of this kind of function in this integral sense. So the resulting value here should be the norm of some function is defined as the square root of the integral of f squared dx, basically. That's the norm of a particular function, and specifically the L2 norm. And then if we have that notion of inner products between functions, if we have some notion of coming up with a measure of a function in this L2 norm sense, we can also come up with a measure of distance, or measuring how far away are these two functions, just by kind of defining this similar idea. F minus g taken in this particular L2 norm sense. All right. So all these things come to bear in basically the context of finite elements. We'll show exactly how they come to bear, but there's a few final definitions for particular sets of functions or function spaces that we'll be using quite frequently over the next week or two. And specifically, I'll point to the particular set or space of functions, sometimes denoted c to the power k. And really, this particular space of functions, ck functions, are really a special set of functions which are themselves continuous functions and whose derivatives up to order k are also continuous. So I've given a simple enough example here to illustrate exactly what this would look like. This isn't quite right. That needs to be modified. But visually, I think it actually turns out quite nicely. So consider some function f, which I'll say belongs to the set of all functions C1, which is to say, C1 is the set of all functions whose derivatives up to order 1 are continuous. What that means is that this function f is itself a continuous function, as you would kind of imagine just by looking at this graph. There's no kind of discontinuities in that function. Also, if it belongs to C1, it implies that the first derivative of this function is also continuous, which we can see directly just by looking at this graph. It has this kind of kink in it, which means that it's definitely not smooth at that point, but it is still continuous. And that's the thing I want to distinguish. A function can be kind of kinky and not smooth, but it's nonetheless continuous. And in fact, this particular derivative is itself a continuous function, but its derivative is not continuous. And hence, if I wanted to say that the second derivative of f being some kind of non or discontinuous function, I say that it is not a continuous function. Itself, it's not even continuous. So it doesn't even belong to the set of C0, or in other words, the set of all functions whose 0th order derivative are continuous, which basically implies C0 is this function itself. That function isn't even continuous, even though this function, it belongs to C0. It is continuous, but its first order derivative is not continuous. So really that's the distinction. If we're talking about continuous functions, we kind of talk about these CK functions to describe functions which themselves might be continuous, but their derivatives might not necessarily be continuous. And it's helpful to distinguish exactly which of their derivatives are continuous and which ones aren't. When does it end? You know, in this case, it's implied that basically the second derivative of this function is not continuous. If I'm saying it belongs to C1, that's kind of the implication. Yeah, go ahead.
The second derivative of function f be
This should be 2x.
yeah,
This should just be 2. Yeah, that's a typo. I was preparing the lectures a little too close to the class time, but thank you for pointing that out. I'll go ahead and make that correction in the slides. But that's the notion of continuous sets of functions. And the last thing that I'll kind of define here in today's lecture is this notion of functions which are square integrable, which is to say some set of functions, I'll say f, that belong to the set of functions or the function space, sometimes denoted L2. That is to say, if I have some function f and it belongs to this particular space, L2, then it is implied that if I take this function and I integrate f squared over this full kind of domain of interest, then I'm guaranteed to have some resulting integral that is basically not infinity. It's not going to blow up. I'm not going to get some kind of undefined value for this integral. And the last thing that I'll do, taking this definition of functions which basically don't blow up when I take, you know, the function value squared and then integrate it over some kind of particular subdomain of interest, I can also define kind of an extended set of functions, which I'll call the space of functions whose integral up to order k are also kind of within this kind of L2 space, or which are square integrable themselves. So if I'm talking about some function that belongs to some set H1, H named after Hilbert, the name of this particular type of function space, really when I'm saying f belongs to H1, I'm saying that f itself is square integrable. I can basically compute its kind of square and then come up with an integral value that's finite. Its first derivative is also square integrable. So I can plug in the first derivative of this thing, take its square, and then take the integral, and I'll get some finite value. However, its second derivative is not necessarily square integrable. It might have some kind of discontinuity, or it might have some kind of singularity that means I don't necessarily get some kind of bounded or non-infinite value when taking the integral of the second derivative of this thing and taking its value squared. So that's kind of all the things that I want you to know about spaces, sets, and, you know, function spaces in particular. So a lot of heavy mathematics stuff. If you were an introductory kind of course on mathematics, you know, you might be taking a course in analysis or real analysis or functional analysis and all these good things. And they would bombard you with a ton of even more kind of heavy duty symbology and even more abstract concepts. I happened to sit in on such a course, and it was, you know, I don't recommend it. But so hopefully this gives you the absolute minimum amount of knowledge that you need to be able to understand some of the concepts that we're going to discuss as they pertain to describing sets of functions, and in particular describing solutions to problems of interest, finite element problems, which themselves are always going to belong to some set of functions. We're always searching for a solution that is a function that belongs to some function space But in order to kind of come up with good solutions to particular problems of interest, we have to kind of impose some constraints on, some of these things. We have to say these functions, they can't just be some random function that doesn't have these kind of constraints imposed on it. They have to maybe satisfy some of these conditions. So you'll see exactly where that comes into the picture. We'll kind of take a step away from the very mathematical treatment that we've taken over the past couple lectures and actually get back to some of the physics. Actually talk about what are the problems that we're really trying to solve, and how do we apply this new language that we've developed to try to actually solve these real world physics problems. So that'll be next time on Friday. In the meantime, feel free to drop by office hours if you have questions on the homework. Otherwise, I'll see you all on Friday.